Hello, welcome everyone. My name is Matheus Bernardino. I am based in Brazil, so long flight here, but good to be with you guys. I work for Qualcomm, contributing to the QEMU project, where we support our Hexagon DSP architecture. Today, though, in this session, I will talk a bit about another software that I'm very fond of as well, which is Git. I've contributed to Git for about 3 years, working mainly on performance improvements and parallelism in checkout command, grep, sparse checkout, parallel checkout. If you guys want to discuss any of this later, we can hang out at lunch. But usually when we say Git, the first thing I usually hear is things like that. Usually people just crawl down and cry, and Git is hard and difficult, or I just remove my whole repo and clone again. I think everybody of us have been there, or are still doing that. And yeah, I do agree, Git is not the most user-friendly tool, but also what I think is Git is a kind of software where the user interface and its internals get quite intertwined. So in order for you to master the tool, you need to really understand how it's built, how its mental model works, what data structures it operates upon. And the idea of today is to show a little bit of that with you guys in this first part of the presentation, so a little peek under the hood of how Git works. And then I will showcase some commands as well, which I think are very useful for navigating your code, especially in a new code base where you don't know much about, and also how to debug code on code bases that you already own and work on a daily basis. So starting very simple, just to make sure we are all on the same page. When we talk about a Git repo, the your left side, you see what is a working tree, and that is where your project files reside. Inside your working tree, you normally have what is called a Git directory, or a Git dir for short. And that's where Git will store all the metadata, all the historical information for your files. If we look specifically on this cylinder there, the object store, that's how Git stores the data. So everything in Git is an object, your commits, your files, previous versions of it, previous versions of the trees. And those objects, they are stored in a very well-compressed format, which started back then when Linus was working on it. And they are referenced by their hash, their SHA-1 hash, right? So you can think of it as, like I said, they're as an on-disk hash set. Here's an example of how a simple repo would translate to objects in Git. So there on the left side, you have a repo which has a README file, a source directory, and inside that source directory, you have 2 Python files, right? In Git, when you git add that stuff, Git would create the following. So you have, first of all, a tree object. And this tree object has 2 entries, one for the README file, another one for your source subdirectory. Then for each one of those, you have a pointer to other objects. In the case of README, that's a blob, a binary large object, which is where the contents of the file will be stored. And in the case of source, you have another tree, which represents the subdirectory, right? So something interesting to see here is that the file contents and the file metadata, they are stored separately. Like the file name and the permissions, those are in the in-tree object, and the contents are stored in the blobs, right? Now, what would happen here if I decide to modify my README file and commit that? Oh, right, I forgot to say, a commit is a snapshot of the whole project at a given time, right? And a commit also has information like the author, the committer, the date, and so on. So now if I were to modify README and commit it, Git would create a new commit. We would have a new root tree representing the project, a new pointer for a new blob that represents my new README file. But as you can see, the source directory hasn't changed from one revision to another. So the object is still the same. The hash will be the same. So of course, Git doesn't have to create a new object for that. And so we just reuse the old one, right? That's more or less how that goes. And you can see as well that there is now an arrow going from this commit to the first one. So Git, that's how Git tracks branches. You have a parent to your, pointer to your parent commit, and so on until you reach a root commit, which has no parents. All right, that's the object storage in a nutshell. So now we can go one level up of abstraction and talk about branches and references. References in Git are, you can think of it as labels. They are mostly it. So either tags or branches, they are labels. And you have a special kind of reference, which is head, which is called a symbolic reference. The only difference is that instead of pointing to an object, it points to another reference. And head is the one that we use to track what's the current state of our repository, right? So as of this moment, we have this repo checked out at the main branch, and the main branch has 3 commits in it. All right? Everybody with me until now? All right. So I can create a new branch, and that's basically it. If I do git branch feature, Git just put another label there, the same commit that my head is. I can check out, I can create a new commit, and that would advance my main and head labels, but not the feature branch, of course. Now, I can check out as well to the feature branch, and I can commit there. And there you can see we start to see some divergence, right? Now, what happens if I check out to a commit itself, not to a branch? You can do that, right? That's what Git will say. That's when Git will say you are in the detached head state. Normally, when newcomers start using Git and they see this big warning message, you are in the detached head state, they think, OK, I messed it up. Let me remove the repo and clone it all again. But that's not usually how that works. So what Git is telling you, it's basically, look, your head is not pointing to any reference. It is pointing to a commit. So if you create commits here, which you can do, by the way, but later, when you check out back to your branch, as you can see, the commits you made there, they are not reachable by any of the references in your repo. So eventually, when Git runs its garbage collector, it will remove this object. It will remove this commit. That happens about some weeks, or depending on your configuration, the amount of commits you make, it may happen before, especially now with Claude and things like that, where we commit a lot. So the warning there that Git makes is to help you remember that if you want to keep that commit, please create a branch on it, or a tag, or whatever. That's basically it. Now, we can also delete a branch with git branch -d feature. And what that does is it simply removes the label. The commit is still there. It's still reachable. You can use a thing called git reflog. How many of you have heard of git reflog or use? All right, good. Seems like we are split in the middle here. But yeah, git reflog is a log of references. So all your references, main branch, feature branch, even the head reference, all of them have a log associated with them. So you can run git reflog head, for example, and you can know everywhere your head has been. It would be nice in life if you can know where everybody's head is, right? But yeah, that's useful to recover data. And I will talk a little bit about that in the second part, but just so as you know, that commit is still recoverable. Now, what happens if I want to git revert? Instead of going back, you just create a new commit, which is the inverse image of the one you are reverting, right? That's good because you don't rewrite history. And as anybody that has worked with Git with other people know, rewriting history can sometimes cause troubles to your team and to yourself. If you reset, on the other hand, that's when Git will take the branch and the head and put it back on the other commit. So those commits after is as if they never existed, though, of course, they are in the repo, and you can always retrieve them. I can also create a tag. And the tag, you can check out. But the interesting thing is that if I create a commit there, I will be in a detached head state, as we saw before. Because tags are pretty much like branches, but they are fixed in point. So you cannot move a tag. Of course, you can delete the tag and create it again in another place, right? But the idea of the tag is that it's fixed in a specific object, usually a commit. OK, the last part of this first part of the presentation, I want to briefly mention merge. That's a real story from our team. Our team is here. So git merge, how does that work in a nutshell? Basically, you have 2 branches. Git will look into the tip of the 2 branches and the first common ancestor of these two tips. So that's what's called a three-way merge, because there's essentially 3 commits being analyzed in this whole process, right? Something to remember here is that Git will only look at the tip commits, not the ones in between. So for example, here, if I had at the start a file that only had the A line, then I added a B, removed the B, and then I merged that with another branch that only added B, B will be there at the end, because Git doesn't know what happened in between there that you added and then you removed. It only knows that on the first branch, B was not present. In the second one, it was, so it merged and puts B there. Differently from merge, we have a rebase. And what a rebase does is it replicates those commits from the branch you are rebasing onto a new base. And you can see there that the hashes have changed. So those are new commits. Why is that? Because you changed the outer, the commuter, and the commuter date. So those are new objects, which the hash for is different, right? And also, there could be conflicts there that you had to manually resolve. So those could be different. All right, that was an initial introduction to how Git works in a nutshell. And I want to spend the next part of this talk talking a little bit about ideas of what you could use to better navigate your code with Git and to better debug it. Maybe some of the tools I will show here you are already familiar with, maybe you're not. But something that I was even discussing with my team earlier today is that we had this question in mind, like, why should I learn Git nowadays if I can just ask Claude or Cursor to run the commands for myself? And I mean, you can do that, but that's why I think it's important to understand the mental models that I just showed before, because then you can ask Claude to do what you want and know that it's doing it correctly. If you just rely on it, you'll probably eventually face bad configurations for your repos. Anyways, first thing I want to talk about is pathspecs. So this word means path specifications, and it's the way Git you can specify a collection of paths to Git. It's pretty much like we are used to in our bash shells. You have wildcards, for example, and there you can see, for example, the first one will take all the JSON, the JS files, the JavaScript files, as we are familiar with. But I think it's also very useful to use the double star ones, such as the third one there, for example, where you take all your .c files in any part of the hierarchy of directories that start on the test directory. Does that make sense? So that's what those wildcards do. You have bracket expressions, just like you have in your shell as well. So that would get you the logger.c and logger.h. And what's interesting that you have in Git, but you do not have on your shell, are those magic signatures. There are a bunch of those. You can check the man page to see all the list of those. But those 3 are the ones that I at least use the most. The magic signature, you put a colon, the signature, and then the path you want to specify. The first one is the signature for root, so just a /. And that's useful, for example, when you're running a Git command inside a subdirectory in your project, and you want to do the operation from a file that is in the root directory, right? So I want to know the status of my README file on the root. I can run with that magic signature. The other one, it's a negation signature. So I can use that to tell Git to handle all the paths except by those ones. I use that a lot, for example, when I'm Git grepping stuff. And I don't want to, I know that it's going to be a lot of hits on our markdown files, for example. But I'm actually grepping the code. I don't want to see the documentation right now. So I usually just use that pathspec to say, Git, I don't care about the documentation right now. Just grep the normal paths. And the other one is a case-insensitive search. So you can use, search because I'm thinking about grep. But you can use that for any Git command, right? You can git add with case insensitive, for example. 2 tips there, just you should use the single quotes to avoid shell expansion on those. And I put a link there to the place in the man page where you can find more about pathspecs. That man page, if I'm not mistaken, is man git glossary, which for those who don't know about is a man page that also has all the nomenclature that Git uses and explanations for that. So I just talked about grep. Who of you already use git grep? OK, just a few. Interesting. Who have heard about rip grep? Oh, nice. Cool. So rip grep is also a very interesting alternative, especially performance-wise. Rip grep is famous for being faster than any alternative. But git grep has had some work done to make it faster, especially with parallelism. That's part of what I worked on. And what's interesting about git grep relative to GNU grep is that it's recursive by default, and it can search past revisions. So you can grep for another commit or another branch. Oh, and of course, it honors your git ignore and your git directory. Yep?
Is that git space grep or git dash grep? I see.
Git space grep, yeah. So there are two examples there. The first one I'm grepping just in the working tree. Can you see in the back there? Is it OK? All right. Thanks. And the second one, I'm grepping a historical version, past commit. Now, it can get way more interesting than that with some options. And that's where I think Claude can be a good assistant, for example. You don't have to memorize these kind of things anymore. But if you want to know, so -n tells git grep to put numbers. The heading and break will separate each occurrence by the file it was found. So that's a nice way that you can quickly scan your whole repo for something that you are looking for and know the file it is in, which other occurrences are there. That's one way to use git grep. But I personally like this one very much. -w, this one means function context. So anytime it finds an occurrence, it will print you the whole function where that occurrence has been found. In this case, maybe I didn't select a good example because I was grepping for the function name. But for example, here, I could have grepped for repo submodule init, and it would give me this whole function where that one is being called. That's very useful for code navigation. Blame. So blame takes a bad reputation of being used to, well, blame your colleagues. But it's way more than that. I think it's very interesting and useful tool to understand how that specific line has changed over time and who has last changed it. And of course, there are some limitations to that. As I mentioned there, sometimes, for example, you are trying to understand a piece of code that doesn't make a lot of sense. And you say, let me git blame it to read the commit message and see what the people that developed this were thinking. But the blame would give you the last commit, which was just, I don't know, a space modification or a variable renaming. A new parameter was being added to the signature of a function. So it can have some drawbacks when you use blame. However, I will mention two things which are, oh, that's really small. Anyways, it's a demonstration of TIG blame. Who of you know about TIG, T-I-G? OK, so TIG is the textual interface for Git. It's another project which uses Git as a backend. And it can run a lot of commands. One of the most useful to me is TIG blame. So you can run TIG blame on a file. And what that will do, I will wait for it to start again, because it's a GIF. But basically what it does is you can blame line by line, and you can interactively select a line that you are interested in. You can see the commit that was there. And if that's not the commit that you wanted, you can hit comma, and that will go to the parent commit. So you can interactively blame a line until you find the change that you are interested in. Okay? I've used that a lot when I'm starting at a new repo in a new team that I don't know much about, and I'm having a hard time to understand a specific line of code. So usually, if the team, of course, maintains a good commit message hygiene, that can be a very useful source of information. Now, I mentioned blame, but I want to mention something that goes in the opposite direction and can help you also find changes to a specific file. We think about log as a way to see the commits over time in a branch. That's how it was designed to work. But there are much more features hidden there. So there are some options which I listed there I think are very useful for code navigation. You can use a pathspec. You can limit by date. You can use grep, not git grep, git log -- grep. Git in its many different ways to specify things, but to grep into commit messages. So for example, I want to list all commits that have the word co-authored by Claude. I don't know. You could use grep for that. Git log -- grep. You can limit it by hash. You can use graph to see how the branches come to be and how they evolved over time and got merged. You can use -p to only not show the commit message, but also the diff associated with it commit. And finally, there is the format flag, which can help you put the output that you want, customized. Now, there is a feature in GitLog called pickaxe, which this is the one that I mentioned is kind of the opposite from git blame, because this one you can see from the start instead of from the end. I'll explain what I mean just a minute. So you have log -g and log -s. Together, those two options, they form what the Git community call the Git pickaxe framework. And git -g, log -g, will show you all the commits whose diff contain a specific string. -s is very similar. The only difference is it will show you the commits whose diff contains the string you're searching for, but the number of occurrences of it have changed. They are even. Why does that matter? For example, I want to find when this show_module function was first introduced in the code base. That's the command I can use for that. Git logs -s reverse. So it will list the commits from the root, from the past until now, all of them who have introduced or removed one occurrence of the show module function. Make sense? No, not that much? I can explain in other words, maybe. So for example, -g, if you do git log -g some string, it would show you a commit which just took that string somewhere and put it in another file. It just moved that string to another file. And that's not sometimes what you're interested in. You want to know when someone added that string or removed that string. So that's what -s is used for. Okay. Yeah, those are two complementary options that you can use. So as for data recovery, I mentioned before about reflog. Here I'm giving an example of running git reflog head. Let me see if I can explain. OK, so on the first column, you see the hashes. It's pretty much just like a git log. On the second one, you see the tags that were there. So for example, right at the top there, head, master, origin main, all of them were at that commit. And then after that, you have an explanation of how your head got into that point. So at the top, head got there through a pull. I run a git pull, and my head was moved to that commit. Before that, where was my head? My head was at that 7c2 commit, and it got there through a git checkout command. What about before that? It was at another commit, and it came to be there by a rebase, and so on. So there you have all the list of the commits your head have been pointing at and how it got there. There's an interesting case there, which I haven't seen when I was preparing the presentation. Do you see that there are 3 commits which are the same there? So that's basically because the pull, rebase, and the checkout command, they all were targeting the same hash. So we just, we didn't do anything actually useful with the commands there. We were just running on this, like git checkout A, and then you run git checkout A again, something like that. Okay. So that's very useful when you want to, when you were in the detached head state, for example, and you committed something you want to recover, or if you just recently deleted a branch and you said, oh, no, that branch was useful. I need to get that back. You can use git reflog for that. Okay? Now, another command used for data recovery, which I just briefly mentioned that at the bottom, is git fsck, which is the same, it's based on the tool that we use, the fsck file system check, right? What it does is it scans your whole object store, and it finds all objects that are dangling, so they are not part of the overall graph. If you can remember that picture that I showed right at the beginning, where we had the trees, the blobs, and the commits all pointing to each other, Git will make directly a cyclic graph, so a DAG. And eventually, some commits, some blobs, some objects, they are going to be dangling from that main commit, main blob, sorry. That's what FCK is useful for. It will find those objects. It will save on a directory so that you can inspect later. Now, when are you going to use this? For example, suppose you run git add a file, and then you said, no, actually, I didn't want to add that. Let me just revert. And then you reset, minus hard, for example. But then eventually you said, oh, no, I actually needed that file. If you've added it, it is saved already. You don't have to commit to save it. When you git add, Git will already create a blob for that in the object store. And that will show up with FSCK. You just have to invest some time to find out exactly what you need there. Now, going to the end now, I talk a little bit about code navigation, how to recover data, and at least I think it's important to mention, I think what is the most useful tool for debugging in Git, which is git bisect, of course. Bisect, as the name says, will help you doing a binary search so that you can find a specific commit which either introduced a bug or more generally changed a behavior you are interested in. So for example, here in the left-hand side, you have a series of commits there. The one on the top called bad, that's the most recent one. And the one in the bottom there called good, that's the oldest one. So suppose I know for a fact that at that good commit, my tests were passing. They were all good, code compiled, everything was fine. The world was great. But at the bad commit, something broken. Clients are pissing us off, saying that something is broken and we got to fix it. You don't know where the bug is. You don't know which commit introduced the bug. What can you do? Of course, you can use GDB, LLDB, Valgrind. You can use whatever tools, debugger tools you're already familiar with. But you could also use Git to find out which commit introduced that bug. And that will help you a lot to reduce the search scope for your bug, to know what the minimal fix would be, right? So what Git allows you to do with the git bisect command is you can say, look, Git, this is my script that will tell you whether a commit is good or bad. This is a commit that I know it's bad, and this is a commit I know it's good. Now find out where the inflection point is in that branch. And Git will do a bisection as it's shown there until it finds the culprit. Now, as I mentioned, this is often marketed as a very useful tool to debug code, which it is, but it's also very interesting to know when a behavior changed, not specifically when a commit is good and a commit is bad. That's so important that recently, I mean, it's been a few years, but anyway, they changed the nomenclature in Git so that you can either use good or bad, and you can use new and old as well, because they realized that bisect was much more useful than what it was originally intended for, right? And I've used that in our team in the past, for example, to know when we changed a specific API that didn't break any tests, but someone else was depending upon. So I did a small script that only grabbed for a specific signature and until we find what was the place. All right, coming to an end, here are some references which I think are very useful if you are into this topic. The first one is a blog post that tells about Git archaeology. So it basically tells how you can use Git as a tool to explore how the code have evolved over time. He will mention many of the commands that I show you today, but he has a little bit extra information there. The other one, Git as a debugging tool, is in the same line. The third one is the one I think it's the gem of knowledge inside the Git community, the Git Pro book. It's available online for free in many languages. If it is not in yours, you can translate it. It's open source. And the Git Pro book covers from how to use Git from basis to the Git objects, as I mentioned before, to references, to even more complex and hard stuff like pack files, if you ever heard of those, and communication protocols with the server. This book is amazing for you. Finally, the fourth reference there, that's the golden standard blog post that everybody references others to when they're talking about good practices with commit messages. Everything that I told here today about grepping, searching the log, bisecting, it only really matters if your team has a good habit of making atomic commits, of writing good commit messages, of describing the changes. Not only, there is a difference between describing what the commit does and why it does that. What the commit does, I as a programmer can look at the code. I can see what the commit is doing. But why is it doing that? That's what the code won't tell me. That's what you as a developer should tell me in your commit message. So all of these things, which I think are very useful, but unfortunately couldn't make it to this presentation, you can see in that last blog post as well. Thank you. This is my website. If you want to have, I have some other blog posts about Git as well, even how to make a commit without Git, if you're interested in that, and other things there. And thank you. So we have time for any questions or comments, if anyone got into that. Yeah? Do you have a mic or? Thank you. I think it's the light.
Back in the section where you were doing things with git grep, you mentioned how you like to use the function awareness, or I forget what exactly it's called, where it shows the whole function. Yeah. Is that LSP aware, or is that just generic based on general syntactical rules?
Great question. That's based on regular expressions. And I am one of those who say that regular expressions are write only. So once you write it, you never know how to read that anymore. But there are folks in the Git community who are maintaining those regex for a lot of different languages, even for Markdown, for example, so that you can have the context of the block where you are searching for. It's all open in the Git code as well. Great question. Any other ones there?
Could you give an example of using git bisect? Because I'm curious how you would give it the context of like what behavior is changing, or the break that you're looking for.
You mean a live terminal example, or do you mean a?
Hey, I would take it, but I won't put you on the spot either.
Okay, I think I would prefer not to embarrass myself here with the.
Reasonable.
But yeah, you can say. So what git bisect will do is, you say the good commit, you say the bad one, which one they are, and it will check out it commit and run a script for you. You choose the script. What I usually do, I put in my script make and make test, for example. So I want to make sure, I want to find a commit that either doesn't build or build but doesn't pass all the tests. Hopefully, if you had a good CI/CD, you have already gotten this before the merge. That's not usually the case. So usually that's what I do, and the context, basically, it will check out that commit. So the script, I just run make and make test, and it's all good, usually. Does that answer your?
Yeah. Thank you.
There's one over there.
I just wanted to mention something about git bisect that took me too long to learn and is very helpful, which is if, for example, you have a bug where there are certain commits where you can't test it either yet because it doesn't compile on those, or there was some other bug masking it, you can use git bisect skip if you don't know whether that commit could be good or bad. And then at the end, it will tell you if it thinks it must have been one of the skipped commits that was bad. Otherwise, you have the problem of you just kind of have to randomly choose one, and you could end up with doing the wrong one and ending up in totally the wrong place.
Yeah. No, that's a great tip, by the way. And if you're doing automated bisecting with the script, as I mentioned before, you can just exit with a specific code, which I don't remember, which is maybe 125, I think, from your script, and that would tell the bisect machinery, skip this commit. So yeah, that's very useful. And in that case, your Git is doing a best effort, right? It might not find the exact commit that introduced the bug because it might be one of the ones that you skipped. But still, it's a very, very good one, yeah. If you know, yeah?
Suppose I have a situation where I committed something but haven't pushed it yet and made more commits after that, but the thing that I committed at that point contained something that should not have been there, say a credential.
Yeah.
Is there a way to essentially fix that before pushing?
Yeah, certainly. Before push, you can use a rebase with -i, which is the interactive rebase, and you can just delete that commit. But of course, that only works if everything is local on your machine. If you have anything pushed, it's gone. Yeah. Oh, great.
I have a question about large repositories, ones that have tons of commits, tons of files. I understand that Git has some features like sparse checkouts, but oftentimes my experience has been that those are not very ergonomic. I'm curious, in your experience, what has worked well and what hasn't?
Specifically to handle a lot of files. Is that okay? Not exactly large files, but just large. There's just a lot of the number. Okay. Yeah, sparse checkout. It's a great feature. By those of you who don't know about it, you can basically tell Git, I'm only interested in this directory of the whole repo. So whenever you do any operations, just consider this directory. And it will just check out that one. It will grep that one, log that one, and so on. It's a great idea, but as you said, ergonomics, not always the best. It's a recent feature, kinda. It's not been so long since it has been there. And there was at least 2 developers from Microsoft who were actively contributing to make sparse checkout better. The last I heard from it, because I've been away from the community for a while now, but the last I heard, they were making very good progress to the point that sparse checkout was already useful with other hard or complex features like submodules and things like that. But still, is a work in progress. So I know sparse checkout may not be always the best solution. I personally have used it a lot. I use it in combination with Git work trees as well. And to my usage, it has been very good. I have stumbled upon some use cases, some corner use cases, like using Git work trees with submodules where I had some hard time. But still, for more common scenarios, it has been quite good for me. Yeah. I think that if that's all. Oh, there's one more at the bottom.
So imagine a scenario where you've got a feature branch and you're trying to rebase it on main. And for the sake of the example, let's say main has moved forward 10 commits, and I'm going to get merge conflicts at, say, 3 of those, but some subset. And they're going to be really hairy to untangle. And what I find myself doing usually then is like trying to do these partial, like I'm going to guess that these are not going to create a merge conflict and like rebase partially in there. So I've got like some progress, and then like try a hard one so I can bail out. And is there any tool that can like make this easier?
Interesting. There might be third-party ones, but as of native Git, I don't think there is. What I know you can use, but not for that specific use case, is Git re, worst name ever, which stands for Git restore. I always forget that. Never mind. Does somebody know there? No? OK. So what it basically does is if you rebase a branch often, for example, a side branch that you want to keep close to main, but you are rebasing it from time to time, you can actually save the conflicts and the resolution in Git using Git re. And when you rebase the branch again, Git will say, hey, there was a conflict here, but I remember how you last resolved it, and I'm using the same resolution, if it's clean, right? If it's not, you have to intervene. But I don't think there is such a thing, at least not native. Yeah.
OK, thank you.